So I think we'll start the final session of the workshop. So thank you to everyone for coming along to the final session. So the first talk will be by Valentin Buciumaș, and he's going to talk about p-adic representation theory and special functions. So over to you, Valentin.
Great. Thank you for the introduction. And I'd like to thank the organizers for inviting me to give a talk in this conference. Since this conference is organized by Matrix, I guess I can say that it's a pleasure to be back in Australia, even though it's virtually and not in person. And I really hope Matrix will continue to organize such conferences even after the pandemic is over, and then I might actually come back to Australia in person. So that would be great. Okay, so today I'll talk about p-adic representation theory and special functions. So what I want to do today is I want to give a very, very, very brief overview of how one studies representation theory of p-adic groups. And I want to focus on how certain special functions appear in this topic. And then I also want to try to explain how one might study such functions combinatorially. Okay, and related to the name of the conference, I'm not sure about finite temperature, but I can assure you there will be combinatorics and integrability in this talk. And I also do want to mention that most of the work that I'll present towards the end of this talk will be joint work with Ben Brubaker, Dan Bump, and Henry Gustafsson. But much of the work in the first part is just something that's well known for quite a while. And of course, if you want to, feel free to interrupt me during the talk or write questions in the chat. All right, so let's go on. So how do you study the representation? What is the representation theory of p-adic groups? So generally you start with a group G, and throughout this talk we'll mostly focus on GLR over QP, but most of the things I say in the first half will hold more generally, for example, for G reductive split over F, a non-Archimedean local field. But for simplicity, I'll just talk about GLR over QP. The idea is you want to study complex, smooth, admissible representations of this group. So what does this mean? Complex simply means that the representation V is a vector space over C. So this is somewhat different than other types of representation theory you might be used to. For example, if you study the representation theory of GL over GLR over C, if you study the complex representation theory, both the group and the vector space will be defined over the same field. You might also want to study modular representation theory, and in this case, the field will be a field of characteristic P. But again, both the group and the vector space will be defined over the same field. In this case, this is somewhat different. So the group, we take the QP points, but the vector space is complex. And then there are two more technical requirements. You must have that for any vector V in the representation, the stabilizer has to be an open subgroup of G. And for any open subgroup of G, the space of K fixed point has to be finite dimensional. These conditions can be reinterpreted in terms of the topology on G, which I don't want to define in this talk. I do want to say that the topology is a bit different than the topology, for example, on GLR over C, because the topology or the metric on QP is somewhat strange. But maybe let's not go into these topics. So let me do say that the representation theory is different than both the modular representation theory and the representation theory over C. So for example, if a representation satisfying these three properties is irreducible, then it can only be either one-dimensional or infinite-dimensional. And the one-dimensional representations will just basically be characters of powers of the determinant, and they're considered somewhat trivial. So essentially, all the interesting representations of this type will be infinite-dimensional. Okay, so why should we study such representations? There are many reasons. You might argue we should study them just because they're interesting by themselves. But one of the most well-known reasons is the Lagrange program. And one of the basic parts of the Lagrange program is what's called the local Lagrange correspondence for GLR. And this states that there is a canonical bijection between two sets. So on the left, you have exactly this type of representations, and they must be irreducible. And the correspondence says that these will be in one-to-one correspondence with certain representations of the Weil group with some extra data. This is what's called QP semi-simple R-dimensional Weil representations. I won't define what these things mean. I just wrote this as some sort of motivation, why we care about this part. This bijection is somewhat important if you're interested in studying automorphic forms. And for example, this canonical adjective here, what it means is that this bijection somehow behaves nicely with respect to several things. For example, it preserves L factors or epsilon factors, and maybe it behaves well with respect to going from GLR to GLR minus 1, and so on and so forth. So this is some motivation as to why I would be interested in this set. And now the question is how to study such representation. In general, this is a hard topic. And one way to simplify it is to work with Hecke algebras. So the idea is the following. A Hecke algebra in general is for any K open subgroup of G, is just the space of compactly supported K bi-invariant functions on G. So this means functions from G to C, such that this fk1 G K2 is equal to f of G for any K in K and G in G. And the idea is that if your group G acts on some representation V, then HK will act on the K fixed points of V. This is generally very useful because you can translate the representation theory of G into the representation theory of HK. And in general, these spaces will be finite dimensional. So you turn an infinite dimensional problem into a finite dimensional problem. What's not optimal about this is that this is useful only if V has a K fixed vector. So if V doesn't have a K fixed vector, then this will map V into 0. So you don't obtain any information. So the Hecke algebra, if the representation V has no K fixed vectors, the Hecke algebra doesn't see that representation. So the Hecke algebra will allow us only to study a certain subset of these representations. And depending on the subgroup K, we'll have a different subset of representations. And generally speaking, as you start learning about p-adic groups, there are two very important examples of Hecke algebras. And these are the spherical and the Evaporative Hecke algebra. So now let me go through these examples. So first is the spherical. So we take K to be the spherical subgroup of G. This is just G where we plug in ZP instead of QP. And by this procedure here, we obtain what's called the spherical Hecke algebra. And now what happens is we have a bijection. So this procedure here produces a bijection of irreducibles between irreducibles of G with all the properties that I mentioned above that have a k-fixed vector and irreducibles of the spherical Hecke algebra. These representations of G are called unramified. And they're very important. So they're the simplest type of representations, but they're very important in the representation theory of p-adic groups. So for example, if you have an automorphic representation, you can break it down into a representation for every prime p, maybe plus something else. And all but finitely many of these representations for these primes will be unramified. So once you understand these representations, you almost understand automorphic representations. It is true that in fact you don't fully understand them, but it's still pretty important. Okay, so now one may show that this spherical Hecke algebra has a basis indexed by dominant weights lambda. So it will look like the function that's 1 on this double coset and 0 everywhere else. And then this is the first place where special functions appear in the representation theory of the p-adic group. One may show, so the Satake isomorphism tells you that you can identify the spherical Hecke algebra with W invariant functions on the co-weight lattice, which can be identified for GLR with symmetric polynomials. And this also happens to be the same as the Grothendieck group of the category of representations of the dual group over C. And now this basis element gets mapped to H lambda. So H lambda is a polynomial in x1 through xr. This is what people call in type A the Hall-Littlewood polynomial. And generally speaking, it's also called McDonald's spherical function. This polynomial, the Hall-Littlewood polynomial, also depends on some parameter, which some people might call Q. This parameter, so for this equivalence to hold, this parameter has to be equal to the cardinality of the residue field on the p-adic side. So for QP, this would be just P. So if in the Hall-Littlewood polynomial I set Q to be P, then I get an expression for this basis element of the spherical Hecke algebra. Okay, so this is how Hall-Littlewood polynomials appear in the representation theory of p-adic groups. So now we may go on. Any questions so far? All right. So moving forward, the second most important, or another second important Hecke algebra is the Evaporative Hecke algebra. So instead of working with the spherical group, we work with the Evaporative subgroup. The Evaporative subgroup will be something that looks like this. So in particular, we will work with CP on the diagonal and above it, and PZP below the diagonal, or GLR. But this can be defined in general. It depends on the Borel and on a projection between CP and the finite field FP. And this produces the following Hecke algebra, what's called the Evaporative Hecke algebra. This is what other people might know as the extended affine Hecke algebra. So the affine Hecke algebra, for example, for SLN is a Coxeter group, is a deformation of a Coxeter group, and you can write it in terms of generators and relations. The extended affine Hecke algebra is the Hecke algebra for GLR. This is not the deformation of a Coxeter group, but it still enjoys many of the same properties. So now what happens is a result of Borel says that there is an equivalence of categories between the G representations that are generated by their Evaporative fixed vectors. These are what's called tamely ramified representations. So this category is equivalent to the category of finite dimensional representations of the Evaporative Hecke algebra. And this equivalence has quite a few interesting properties. So for example, it respects induction. So on this side, you may induce from a levy. So you may induce, for example, for GLN cross GLM into GLN plus n. On the right side, you also have induction on the Hecke algebra level. And this equivalence of categories respects that structure. Okay, so now moving forward, a second topic of interest in the representation theory of p-adic group is the Whittaker function. Whittaker functions are certain functions from G into C that are n psi invariant. So in particular, this means they behave, so if you have phi of ng, this will be equal to psi n phi of g, where psi is a certain additive character of the unipotent. So n is the unipotent, which just means the set of matrices with one on the diagonal and anything else above and 0 below the diagonal. Okay. And these Whittaker functions appear permanently. So for example, they appear as Fourier coefficients of holomorphic forms, or alternatively as constant terms of Eisenstein series. So one thing you might want is an actual combinatorial formula for these Whittaker functions. You want to be able to compute. So now here is a setting, maybe something that some people are not used to. You may define the space MK. Well, some people call this the spherical Whittaker space. This is the space of complexly supported functions on G that are right K invariant and left n psi invariant. So what this means is that this is a set of all f from G into C, such that f n g k is psi n f g. So this space here contains information about the Whittaker functions. And it is easy to see that the spherical Hecke algebra acts on this space, because so this space has right K invariance, and the spherical Hecke algebra has left K invariance. So there is an action by convolution of HK on MK. And more so, one can show that M is a rank 1 HK module. So this means we can identify MK again with symmetric polynomials. And this is as an HK representation. And then there will be a certain special elements in this space MK. And by the Casselman Shalika formula, these will be mapped into Schur polynomials. So this is the second appearance of an interesting special function in this theory of p-adic groups. So the Schur polynomial appears as in relation to the Whittaker function. Now, this formula here is equivalent to another formula, which was actually the first thing that Casselman and Shalika proved. This is a formula for the spherical Whittaker function. The formula says that certain values at elements that depend on lambda of this spherical Whittaker function will be equal to this quantum factor times the Schur polynomial. So here, pi to the lambda is just a diagonal element in G. And lambda has to be a dominant weight. And there are many conventions. So sometimes this will be a minus lambda. Sometimes people take a plus lambda. That's not very important. Okay. So this is the spherical Whittaker function for which we have a formula. Now, other objects people are interested in are the Evaporative Whittaker functions. So for this, we may consider the following space Mi. This is the set of compactly Evaporative functions, again, which are right invariant with respect to I and left invariant with respect to n psi. And just as before, the Evaporative algebra acts on this Evaporative Whittaker space. And there is a well-known theorem that as representations of the Evaporative algebra, Mi is isomorphic to sign times tensor, the Evaporative algebra, and the tensor product is over the finite Hecke algebra. This result has been known for quite a while, and I was never able to find a place where the proof is written down until recently, when Savin and Chan wrote a paper, I think in 2018, that's now in MathZ, where they actually give a proof of this result. So now, this will tell us about Evaporative Whittaker functions, and in particular, there is a formula for Evaporative Whittaker functions in terms of the Mazur-Lustig operators. And I believe one may show that this formula is equivalent to this isomorphism. So what is the formula for the Evaporative Whittaker functions? One may define these type of de Mazur-Lustig operators. And for generators of the finite file group, so the symmetry group, for each simple reflection SI, one may define these de Mazur-Lustig operators. These act on the space of polynomials in X1 through XR. And here SI is the operator that switches between switches between Xi and Xi plus 1. And if so, these operators will respect the braid relations, and because of this, for any W in the Val group, we may write it as a reduced expression, and then we may define TW as the product of TS1 dot TSN. And now this is a result of Brubaker, Bump, and Licata. The Evaporative Whittaker function depending on W, an element in the Val group, evaluated at a certain element depending on lambda, will be this de Mazur-Lustig operator TW applied to x to the lambda. So here x to the lambda is just x1 to the lambda 1 times x2 to the lambda 2 times dot dot. And by using this de Mazur-Lustig formalism, one may relate this Evaporative Whittaker function to a non-symmetric Hall-Littlewood polynomial. And the relation looks something like this. So this is the Evaporative Whittaker function, evaluated at an element depending on lambda. And on the left side, we have some stuff. And then this is the non-symmetric McDonald polynomial, where one of the variables goes to infinity, which then becomes, so this thing becomes essentially the Hall-Littlewood polynomial. And I want to emphasize that everything on this page is not type A dependent, so it works in general type. Any questions so far?
So you would call that an Evaporative-Whittaker function?
This thing here, yes, I would call it an Evaporative-Whittaker function.
Great, thank you.
I haven't defined it, so sorry about this, but yes, this is, I guess we can argue this is the definition. Okay, so this is, so basically the point of this slide here was to emphasize that these Evaporative-Whittaker functions can be studied combinatorially via the Mazur-Lustig operators. Now, there is a different way to study these Evaporative-Whittaker functions, and this is by using lattice models. So now I'll try to explain a lattice model interpretation of these Evaporative-Whittaker functions. And starting from now on, so everything that's related to lattice models in this talk will be specific to GLR. So it will not work a priori outside of type A. And this is work joined with Ben Brubaker, Dan Bump, and Henry Gustafsson. So just as before, here we had the Evaporative-Whittaker function. It depends on an element W in the symmetry group, and we evaluate it at an element depending on lambda. What happens is that in fact you may write Evaporative-Whittaker functions depending on two elements W. So one tells you which Evaporative-Whittaker function to look at, just as before. So this W1 is the same as this W. But then you may evaluate this Evaporative-Whittaker function at an element depending on lambda times another element of the Val group. So in general, when people write the Casselman Shalika formula for the spherical function, they only write the values at this element, pi to the minus lambda. And this is because these values are the only independent values, in the sense that once you know those values, you know everything else. But for Evaporative-Whittaker functions, these values are not enough. So the largest amount of independent values will be elements of the form pi to the minus lambda as before, but now times the W2. What's interesting is that this lattice model is perfectly equipped to handle both elements of the Val group. And I'll explain immediately why. So I assume people have seen lattice models in this conference. So I'll go through this topic quite fast, but if you have questions, please stop me. This is like a standard lattice model on a grid. The lattice model is colored, which means that I'm going to start with R colors, and they will be ordered. So I'll have one color larger than the other, and larger than the other, and so on. And what happens is there will be colors starting on the top of the model and colors ending on the right of the model. And the colors will travel, they will move right and downwards. So they will move right like this and downwards like this. Different colors may overlap vertically. So for example, here we have two colors on the same line. This is allowed, but two colors may not overlap horizontally. So I cannot have a blue and a green on this horizontal line here. This model is fermionic, which means I may not have two colors of the same, I cannot have two times the same color on any vertical or horizontal line. So these are the main ideas. So for such a model, now I should explain what are the Boltzmann weights, what happens to the boundary conditions, and what can I say about the partition function. The boundary weights will encode the two Val group elements and lambda, the dominant partition lambda. So first, it is easy to say what's happening on the left and on the bottom. So on the left and on the bottom, there will be no colors. This is the boundary condition. On the right, the boundary condition, so on the right, we have R rows and are colors. So there will be a color on each row. And the colors for W1 equals 1 will be ordered. So if C1 is the largest color, C1 will be here, and then C2 here, and then C3 here. And then for general W1, I can apply W1 to this set of colors, and W1 will act by permuting the colors. So the colors on the right will be the ordered colors permuted according to W1. Now on the top, I have many columns. I have more columns than colors. So what happens is lambda will tell me on which columns the colors will live. So the colors on the top will be on lambda plus rho. So what this means is if lambda is, let's say, 4, 2, 1, rho is then 2, 1, 0. So then lambda plus rho is 6, 3, 1. Okay, so this means I will have colors at 6, 3, and 1. So I will denote this column by 0, this by 1, 2, 3, 4, 5, 6. So this partition lambda tells me where the colors are, in which columns. And then initially the colors will again be ordered. And this is where W2 plays a role. So W2 will again permute the colors. These are the boundary conditions of the lattice model. Then we have certain Boltzmann weights, which are written here. I won't go through too much detail. They're just like you can see them, I guess. What I want to emphasize is that we construct Boltzmann weights via fusion. So what this means, so these are some basic Boltzmann weights when there is at most 2 colors and they don't interact. But what happens if I have the following configuration where I have a red coming from the left going down and a blue coming from the top and going down? What happens is I can break this up into these two, into a product of these 2 weights. And these 2 weights can be computed via this table. And then this will be just a fusion of these 2 weights. And there is a combinatorial way to determine these fused weights. And these will be the weights that appear in this model. The fusion is somehow reminiscent of a certain paper by Alexei Borodin and Michael Wheeler. In that paper, they do fusion, but they understand the quantum group interpretation of these vertical edges. And because of this, they can do a representation theoretic version of fusion. What we have here is a combinatorial version of fusion. It's not entirely clear to us if this is related or not to the fusion presented in the paper by Alexei and Michael. Okay, so now this model is solvable, or as some people would say, integrable. What this means is that there is a solution of the Yang-Baxter equation, namely that the partition functions of these 2 models will be the same. So what this allows you to do is to use this Yang-Baxter equation plus something that's called the train argument to derive functional equations for these partition functions. And it is these functional equations that allow you to match with the partition function with the Evaporative function. So the theorem is then that the Evaporative function is equal to the partition function of a model that depends, whose boundary conditions depend on this W1, W2, and lambda. And to prove such a theorem, one must derive functional equations for both the partition function and the Evaporative function and show that they're equal. And you obtain these functional equations on the lattice model side by using what's called the train argument, and on the p-adic side by using properties of certain G maps, which are called intertwiners. Okay. Now, as I mentioned before, our model is related to and actually inspired by the model of Borodin and Wheeler, their model for non-symmetric spin Hall-Littlewood polynomials. But there are some differences between the two models. In part, one important difference, which I'll focus on, and I'll explain why it's important, is that our model is fermionic, while their model is bosonic. So in their model, they're allowed to have more than one color on the same horizontal line. Our model has also an associated quantum group that's super, so that's GL hat R1. And the model in Borodin and Wheeler is just SLR, so there is no super component to that quantum group. So now one may ask the following question. Why do we care about fermionic if in this model that I presented, all the colors will be different? So basically what I'm doing here is I'm starting with R different colors that are ordered, and I have, there's no way for me to emphasize the importance of fermionic versus bosonic if my boundary conditions don't have twice of the same color. So it is impossible to have two reds on the same vertical line if what I start with on the top is just one red. So at this level, I cannot explain the importance, but I can do it if we go to a different level. So what we could do is we can replace Evaporative functions and instead study paraholic Whittaker functions. So similar to how the Evaporative subgroup depends on a Borel, one may define the paraholic subgroup, which depends on a parabolic subgroup. So a very simple example for GO3, this is the Borel. It depends on, sorry, this is the Evaporative subgroup. It depends on this Borel subgroup. But one may also consider the following paraholic subgroup for the Levy GL2 cross GL1. So then this paraholic will depend on the following parabolic subgroup. And similar to how one defines Evaporative-Whittaker functions, one may define paraholic Whittaker functions. So our system works well if we restrict it to these paraholic Whittaker functions. And it is now that we have to work with several colors that might be the same. So in particular, if I work with a paraholic corresponding to the Levy GL2 cross GL1, what happens is I'll have to work with two colors that are red and one color that is blue. The blue will correspond to the GL1 and the red colors will correspond to GL2. And it is at this level that one must have the model be fermionic. Otherwise, all the theory kind of breaks down. Okay, so this is the model. And then in the very extremal limit, so the Ivahori is the parabol corresponds to the Levy GL1 cross GL1 cross GL1. You might take the Levy GL3, and in that limit you work with all colors, with a model where all colors are the same, and you actually get back the spherical Whittaker function. You get back a model for the spherical Whittaker function. The colored model has some interesting non-trivial properties. Namely, you can derive relations between Ivahori and parahoric functions. So what happens is, an example of this is if you work with, initially you work with 3 distinct colors, you may add partition functions in such a way that you sum over all possible orbits with respect to a certain number of colors. So for example, what I'm doing in this case is I'm going to sum this partition function, and note that here I have a red and a green, and then I'll apply an element, a Val group element, which permutes these 2 colors. So I'm going to get this partition function right here. So outside of this, which is permuted, everything else is the same between these 2 models. And if I add these 2 models, I get now the parahoric model where the 2 colors are now identified. So this will be red, red, but also the top colors will be identified. So this gives some interesting relation between parahoric and Ivahori Whittaker functions.
Let me just clarify. So this is really the sum of these 2, not the difference between them. So it's really the sum of these 2 partition functions that gives you this color invariance, not the difference.
Yes, that's correct. Yeah.
It's a bit unusual because so we have a recent paper with Amol Agarwal and Alexei on fermionic models, and there we observe this kind of color blindness, but specifically with a minus sign instead of the plus sign. So it's like the plus sign is usually what you would expect in the bosonic models, but you say your model is fermionic, so I'm just a bit confused why it's not a minus sign.
So the first thing I'm thinking of is that in general, I think you also work with Lie supergroups, right? With quantum supergroups.
Yeah, in the recent paper, yes.
In quantum supergroups, there's always this difference between plus and minus. So if you work with even components, you might have a plus that when you work with odd components might become a minus. For example, fermionic usually relates to exterior powers, and exterior powers behave differently on these 2 components. So I cannot say for sure without like actually reading your work and looking over my work again. But one thing that might be is that in reality, we might be working with something like GL1R, and you might be working with GLR1.
Yeah.
Okay. So that's an observation. I'm not sure, but that might be a reason why.
Okay, thank you.
Yeah. Okay. So something else we can say, again, joined with Dan, Ben, and Henrik, we can relate using both these formalisms. We can relate parahoric Whittaker functions to certain McDonald polynomials with prescribed symmetry. Similar to how previously we related Ivahori Whittaker functions to the non-symmetric Hall-Littlewood polynomials. These are certain polynomials that have been studied by Baratta and Baker, Dunkel, and Forrester. And now I can write a summary of, how much time I have? Okay. I can write a summary of what we've discussed so far. So we have a table that relates several Whittaker functions with several special polynomials. So if you're not interested in p-adic representation theory, you might be interested on this side. So the relation goes as follows. The spherical Whittaker function, which is the first object you want to study, this is given by the Casselman Shalika formula, which is the quantum deformation of a polynomial times the Schur polynomial. We have the Whittaker function, which can be related to non-symmetric McDonald polynomials in this form. So when I say non-symmetric, I actually mean we have to send a parameter to infinity. So in fact, this is actually a Hall-Littlewood, non-symmetric Hall-Littlewood polynomial. And then we may relate parabolic Whittaker functions to McDonald polynomials with a prescribed symmetry. And finally, there is another Whittaker function due to Jianshu Li. This is a special Whittaker function that he used in his work to study the composition series of the unramified principal series. And by similar combinatorial method, we may actually relate this function to the Hall-Littlewood polynomial. So not the non-symmetric one, but the symmetric one. So for each Whittaker function of interest,
And there's no Q-vile denominator multiplied on that Lee-Whittaker function?
no. There is a Q in the Hall-Littlewood, but no, there's no such thing here.
Okay, thank you.
Okay, so the conclusion is that for every Whittaker function that's of interest on the p-adic side, there will be some combinatorial way of representing it. And then we might study this combinatorially via different methods. Now, when should I stop? Can I have 5 more minutes or?
Yeah, so another 5 minutes is okay. Yeah.
Okay. So everything I said here relates to reductive groups, and in some cases, when we talk about lattice model, to GLR over a p-adic field. And what happens, you can study some more complex objects. You can study what's called metaplectic groups. So I'll try to go through this in 5 minutes. I think the idea is that one replaces G by its metaplectic cover. And then many of the things that I've already said hold true, but now the theory is just a bit more complicated. So for example, we still have some sort of dictionary between metaplectic Whittaker functions and some special polynomials, but now these special polynomials are a lot more complicated. Okay, so very briefly, a metaplectic group is just defined in terms of the group G and the group of nth roots of unity. You can define it via this exact sequence. And then the idea is that multiplication in this metaplectic group is very complicated. It involves, for example, some weird thing called Gauss sums. And one basic fact is that the metaplectic torus T lambda is not a billion anymore. So this makes the representation theory a lot harder. So one of the things that this implies is that the most basic set of representations of the metaplectic group will not have unique Whittaker models. For our purposes, this means that instead of working with one spherical Whittaker function, we will work for GLR with n to the r Whittaker functions. So instead of writing 5 spherical, I'm going to write 5 theta spherical. For theta in some space of dimension n to the r. This is for GLR. And then for Whittaker functions, instead of having r factorial, so r factorial is just the size of the Val group in type A, we will have n to the r times r factorial. So here, instead of writing phi w, we will write phi w theta. And now there are many ways to study these metaplectic Whittaker functions. There are combinatorial formulas in terms of De Maistre-Lustig operators for a certain metaplectic spherical function and certain Evaporative Whittaker functions. So instead of a general theta, I put a sigma here. So what this means is that I sum all the thetas over theta. What I'm trying to say is that this is one special Whittaker function among many. And for this special Whittaker functions, there are formulas in terms of De Maistre-Lustig operators, but now these involve the Chintaganous Val group action, which is a lot more complicated. And these were this is the work of Chintaganous Puskás and Patnaik and Puskás. In the recent work with Dan, Ben, and Henrik, we managed to derive formulas for all Evaporative Whittaker functions in the metaplectic case. So not only for one sigma, but for all theta. And these are in terms of some vector De Maistre-Lustig operators that again involved this these Chintaganous action. And the idea for this came from Lattice model. And I'll try to briefly explain that. There is also an interpretation of this special Evaporative Whittaker function as a limit of what's called a non-symmetric metaplectic McDonald polynomial, or other people call this an SSV polynomial. This is the work of Satake, Stockman, and Venkateswaran. And finally, there are lattice models for all the Whittaker functions. This will be lattice models, and the quantum groups associated to them will be UQ of GL1 n hat and UQ of GL R n hat. So this is joined with Dan and Ben, and this is Dan, Ben, Henrik, and I. Let's see. Okay, so I'm running out of time. So in 1 minute, let me give you the brief overview. Essentially, what we have now is before, for non-metaplectic, we just had colors. Now the quantum group becomes Rn. So we're going to have colors and scalars. Scalars is what we call supercolors. The horizontal edges will have a color or a scalar. There cannot be more than one. And there cannot be nothing. So it has to be one color or one scalar. On the vertical edges, we might have nothing, or we might have a pair of a color and a scalar. Colors move down right and scalars move down left. Colors are fermionic, scalars will be bosonic. So in particular, we might have the same scalar on a vertical line twice, but not the same color. The Boltzmann weights are again computed by some type of fusion. This is how the state of the model looks like. This is a pre-fused state. So what you want to do is you want to take these three rows and fuse them together. The dotted line will be scalars, and the lines will be colors. Boundary conditions are encoded in the same way, but now there is an extra parameter here, theta, and theta will be encoded on the left. So theta will determine how the scalars go out on the left side. This is the model. So now let me briefly say what would be some applications of this work. We already have an application in work with Dan, Ben, and Nathan Gray. And this is a proof of equivalence of two expressions for coefficients of Val group multiple Dirichlet series in type A, which has some application in number theory to this study of these multiple Dirichlet series. And in the future, we hope to prove some Cauchy identities and branching rules. These are generally speaking easy to prove with lattice models, but sometimes hard without lattice models. So number theorists care about these Cauchy identities because, for example, in the non-metaplectic setting, these Cauchy identities appear in the Rankin-Selberg method. But in the non-metaplectic setting, the Cauchy identity is just up to the quantum factor, is just the Cauchy identity for Schur polynomials. So that's very easy to derive. But in the metaplectic setting, the Cauchy identity is not as easy, or at least I personally don't know of a way to try to attack it outside of doing some with some standard technique from the theory of lattice models. So I'll end here, and I want to say thank you. And let me know if you have